Swayam Prabha. Digital India. Educated India.
So, in the last few classes we discussed various points related to mechanical modification of soils involving compaction, in which I said that compaction is possible by using shallow compaction methods and also deep compaction methods. In the shallow compaction methods we discussed various points related to the quality of control, the using various types of equipment for compaction of soils behind backfills, behind retaining walls for backfills and many other applications. Today we discuss some points related to deep compaction. Deep compaction techniques are required when the in situ soil extending to large depths does not meet the requirements of performance criteria. For example, the places like Kerala and east coast, west coast, some areas the soil is very soft, and if you want to construct some infrastructure on them, the settlements are going to be huge and they do not have an adequate bearing capacity. So, what we do is that by using some deep compaction techniques which we will be discussing, we try to stabilize the in situ soil which is for example about maybe 10 to 20 meters below the ground level, as opposed to the shallow compaction where you just compact the soil to about half a meter to 30 centimeters in different layers. Here we need to understand what is the performance criteria expected from the ground improvement technique, and we should also see to what extent one can design it. In this this deep soil improvement is possible by a couple of techniques. In fact, we can classify them into three categories. This is, we can say that ground improvement techniques can be used, like say for example the deep soil improvement techniques one can use by many methods like stone columns, jet grouting, deep mixing, many other methods that we will be discussing. Then ground reinforcement techniques are also possible, where you have micro piles, use of geosynthetics, then even stone columns, many things that use reinforcement function as a main criteria for improvement of deep compaction. We try to classify them under ground reinforcement techniques. And then one can also treat the ground using varieties of treatment methods. Say for example, they can range from lime treatment, any of the modifiers one can use. So, we will just see all of these techniques one by one, and what I would be doing is that each of these techniques I would be presenting in detail in the coming classes, and if possible we will try to look at how the technique is developed, what are the principles of the technique, how it can be done in the field, and if you want to do in the field, what are the precautions one should take, what is the design criteria, what are the case studies that wherein these techniques were demonstrated, all that we will examine, and wherever possible I will also show some video clips of these installation techniques. This ground improvement one can classify again, the following methods, like dynamic compaction is one of the ground improvement techniques. One can use vibro compaction, one can use compaction grouting, one can use prefabricated vertical drains, one can use blast densification. So, we will see some of these techniques in detail in the coming lectures, and in this dynamic compaction I would like to describe what is this dynamic compaction and how does it help. So, we will discuss the technique, we will see how the design could be done, then we will see how the evaluation could be done and what is its effectiveness. So, we will see this techniques, what is the energy transfer mechanism, how what are the stages of compaction, and what type of soils can be compacted, what are the types of dynamic compaction that we have. So, once you do this sort of dynamic compaction, which involves huge weights being dropped onto the ground, there could be ground vibrations generated. So, how do you handle them and what are the design issues? So, we will be seeing one by one some of these points here. So, the technique will be essentially that it involves a repeated dropping of a large weight from a crane. Say for example, you see a crane here and the weight could be, you can see a weight here, and the weight you can design what weight you want, and the weight ranges from 6 to 170 tons. Drop height varies typically from 10 to 40 meters. And the degree of densification achieved is a function of energy input, like the weight and height of drop. We know that the energy can be calculated in terms of the weight and the height of drop, and as well as the saturation level of the soil, fines content and permeability of the soil. These are all some of the important points one should remember, that the degree of densification from the dynamic compaction test is a function of some of these variables like the energy input, the saturation level, the fines content and the permeability of the material. Then these weights of 6 to 30 tons can densify the loose sands up to a depth of about 3 to 12 meters. So, for example, if the depth of compaction that you need is about 12 meters, then one can use this technique. You can see here that this is done in a systematic manner. Either say for example, these are all the tampings that you have, like these are drops, and we have it is systematically done in a rectangular or triangular pattern. Say for example, the patterns could be triangular or square, and then each phase can have a number of passes, and it can be primary, secondary, tertiary. Primary means first of all you just compact in a particular place, you compact like this, this becomes, this is a triangular pattern of 3 meter spacing, and the next in between one you need to compact, because these three are already compacted. So, you would like to compact this, you call it secondary pass. So, this is a primary pass, like 1, 2, 3. These are all, say for example, this is a rectangular, this is a square pattern, this is a primary pass we call it, like 1, 2, 3, 4 you can give, and the central one is a secondary pass. So, you compact them in this manner, you can just see a circular weight about whatever, it depends on the project. So, based on this one can compact the ground to about whatever is the depth one can go, like maybe 10 to 15 meters, one can definitely compact using these techniques. So, the spacing actually is an important variable here. The spacing influences a number of variables, like say for example, if you want to go for large depths, you need to have wider spacing. So, for example, so the spacing between the impact points, we call them, they are the points of impact. It depends on the depth of compressible layer, permeability of the soil, location of the groundwater level. Deeper layers are compacted at wider grid spacing, upper layers are compacted with closer grid spacing. You can see the difference here. So, for example, here you have deeper layers to be compacted, you can see that you have a wider spacing here, as high as maybe 5 to 10 meters, and then you have these lines of influence going like this. Whereas one can go for shorter spacing if you want to what the procedure that we do is that we first compact the deeper layers, then we come up and then see that the same level of compaction is reasonably achieved at top layers as well. What we do here is that because of this compaction, deep craters are formed because of the tamping. These craters may be filled up with sand after each pass, and then there is a possibility that heaving occurs, like a small amount of soil comes out and then around these craters, and which is normally small. And what is the energy transfer mechanism? So, the energy is transferred by the propagation of Rayleigh waves and the volumetric and shear waves. Like we know that there are when you do the impact test, there are 3 types of waves. One is the shear wave, shear, compression, and then Rayleigh waves, like all the 3 waves are present, and the most of the time it is a Rayleigh wave that becomes very significant here. The energy transfer, the thing is, the important thing that we should understand here is that you are trying to transfer some amount of high energy, like the kinetic energy is converted into a potential energy, which means that the kinetic energy which you can calculate upon tamping gets introduced into the soil system, and since this energy is imparted to the soil, it becomes more dense, it becomes more stronger, that is what it means. So, this is a relative contribution of different types of waves here. The process of densification is like how does it get compressed. Say for example, this is a big point, because the thing is people were under the impression that how is that you can compact or consolidate a saturated soil, which is already a saturated soil. If you compact, what is going to happen? Then the mechanism of improvement of dynamic compaction needs to be understood. For example, the soil is essentially saturated, and when you compact it, there is no more what is going to happen. So, what is going to happen is that the compressibility of the saturated soil is there, and then that takes place because of the presence of micro bubbles. Bubbles are there at micro level, small bubbles that can get removed, and then the soil gets consolidated, saturated soil gets consolidated. Then there is a gradual transition to liquefaction and repeated impacts. In fact, there is a tendency of high pore pressure mobilization because of repeated impacts, and if you allow that repeated the pore pressures developed because of the repeated loads, then the process of consolidation is okay. So, what we do here is that you can see that the rapid dissipation of pore pressures due to high permeability after soil fissuring. Sometimes this is another mechanism that is already always presented, that there could be some small fissures in soils that leads to higher permeability, and that higher permeability leads to rapid dissipation of pore pressures. Then there is what is called thixotropic recovery. Like the thing is that you have imparted with time, actually you have there is so much energy imparted into the system, and with time also there is a mobilization of strength because of all these other 3 effects. So, what is going to happen is that in this case you can see that this is essentially a loose soil, and you have probing locations in this manner, and you compact the sample, like you should start from you, as just mentioned, that you impact, like if you want larger depths you have a wider spacing, and if you want shallow depths you want a closer spacing of the tampings. So, the mechanisms of dynamic compaction are that the compressibility of the saturated soil due to presence of micro bubbles is helpful. Gradual transmission to liquefaction and repeated loadings also helps, because this is also accompanied by some pore pressure dissipation later. This is also aided by, say for example, in some cases there could be soil fissuring because of the impact loads, and permeability gets increased. So, these are all some factors that could lead to better improved performance from the dynamic compaction. So, is it applicable to all ranges of soils? So, actually many of these ground improvement techniques, they are all specific to soil. As I just mentioned, you can't use one technique for all soils. like there is no one medicine for all diseases. So, the good thing is it is applicable to wide variety of soils, and then the grouping is done on the basis of grain size characteristics. Say for example, here you see that this is a zone 1 and then the soils are supposed to be pervious here, and plasticity index is in the 0 like cohesive non cohesive soils, and then the grain size distribution is reasonably bigger. We think that the materials that are there in this are best suited for ground improvement by dynamic compaction. Then the zone 3 like impervious materials where the plasticity index is more than 8, say for example clays they are not very effective, and so they all come under this region where the actually the grain size distribution is quite like it is 0.1 less than 0.1 mm, it is in this range like essentially clay material, and in between like say for example the zone 2 what we call it comes, we can say that it is a semi pervious, and then the plasticity index is in the range of 0 to 8, and actually here one should be little more careful in applying these dynamic compaction techniques, and there should be it can't be rapid in the sense that in the case of sands it can be little rapid in the because you are depending on pore pressure dissipation because of the grain size, but here the grain size being little smaller you need to look for delayed time intervals, or if there is another way of improvement of pore pressure dissipation it is okay. So, essentially the many types of soils are very I mean one can improve this many types of soils using the dynamic compaction, and like but then people generally use to compact granular fills, and then they are very much useful for compacting rock fills below water table, and for boundary soils where the other methods cannot be applied or very difficult. Like other methods are not easy, say for example as I just said there are different methods like prefabricated vertical drains cannot be used for gravelly soils, as I mean it is an extreme example, like clays are low, the permeability of the clays is so low that dynamic compaction cannot be used. So, in such a case you go for a prefabricated vertical drains to increase the rate of consolidation because the clays are very slow in consolidation. Then the best application of the one of the best applications of the dynamic compaction is in the case of waste dumps or sanitary landfills and mine waste. Suppose you want to recover some areas for rehabilitation, say for example construction of multi-storied buildings in the outskirts of a city. In the outskirts of the city you have always waste dumps and of course sanitary landfills. So, the thing is what is happening is that waste dumps are quite common, like you maybe if they understand that it is the waste dump is going to be very dangerous, then they convert into a sanitary landfill. So, in either case the waste dumps and sanitary landfills are very good candidates for dynamic compaction, because the waste dumps are they have highly erratic in the sense that all the materials that are considered as waste are dumped, and in the sanitary landfills you cover the dumps, you have a proper lining system both at the top and bottom and in all the sides as well, and you try to have this sanitary landfills, but then once the sanitary landfill is closed you can still after all the biodegradation activity in the landfill is complete, one can use a landfill space, so for example the top of landfill space for construction of a mall. That is a simple example, like if you want to construct a big mall on the top of a landfill it can be done. Then mine waste is something that you have in huge quantities in India or in many places, the like this, how do you stabilize the mine waste, like in many of the bauxite mines, the zinc mines, you have a lot of waste material, you need to handle them in a proper way, so that the say for example there is a slurry of mine waste, there is a there are so many issues there, and one should stabilize the area, and then say for example, NTPC is a classical national power national thermal power corporation. It is a classical example. They generate lot of thermal power, they also generate lot of fly ash. How do you really stabilize the fly ash and how do you make it useful? You know, they can't dump the fly ash wherever they want, they must construct some means of storing them properly, and also if at all they dump, sometimes they must be able to reuse the same space, all that. So, the in sanitary landfills or waste dumps, the settlements are caused either by compression of voids or decaying of the trash material over time. In fact, as I just mentioned, the landfills have biodegradable, degradable, all sorts of materials, like essentially we try to say that, say for example, if you are using plastic and papers, they are not biodegradable, but there could be a green waste, they are biodegradable. So, all these materials are there, and in such a case it is not easy, like I may say some void ratio is there, but what is this void ratio? The definition of void ratio is somewhat tricky when you have biodegradable matter present. You may calculate some void ratio now, but after the biodegradation is complete, there could be something like, you know, the void ratio is because of two components here. One is voids present in the non biodegradable portion and the voids present in the biodegradable portion. So, it is very important that one should understand some of these things properly, and the dynamic compaction is very effective in reducing the void ratio, and it is very useful in reducing the immediate and long term settlement. See, in fact, the problem is when there are so many materials present there, and different materials have different decaying like, you know, biodegradation rate of biodegradation for each material is different. So, for example, in the case of the food waste, it is very fast, but in some other type of organic waste it could be different. So, the rate of biodegradation is something very tricky. So, as long as the materials are biodegradable, you have volume change. So, that volume change needs to be preempted, in the sense if you compact it, definitely already that much, you know, you are able to compact it. So, the post settlements will be much less. So, that is what is meant here, that the dynamic compaction is very effective in reducing the void ratio both in the immediate and long term settlement. Like say if I have a waste dump in somewhere, if I use a dynamic compaction, both immediate settlements are mobilized and long term settlements will also be less. And very important point is that since the void ratio, the dynamic compaction is also effective in reducing the decaying problem, because why the decay occurs, biodegradation activity occurs is because of the availability of the oxygen. Okay. So, it is better that there is sometimes the collapse in the case of these materials, it makes availability of the oxygen less. In fact, of course, as long as the oxygen is available and the biodegradation is complete only, you can be very sure that the consolidation is complete. Then for some recent fields where organic decomposition is still underway, so there is still it is going on, the dynamic compaction increases the unit weight of the soil mass by collapsing voids and decreasing the void ratio. Actually it accelerates many things. What it is trying to do is that, okay, so much of settlements it accelerates. Say for example, if the biodegradation takes say for example 5 years, and if I just do the dynamic compaction, what is going to happen is that all the voids are reduced and the settlements are preempted. Actually this settlements, say for example, you may be expecting about 3 meters, you can expect settlements of the order of 3 to 4 meters. You know, say for example, I will tell you a simple example. The landfill is about 30 meters height, a typical case, and normally the settlements you will be expecting about say for example 5%. So, in 30 meters, like the about the 1% is quite less. I mean, say for example, you will have about how much about 300 mm. So, the settlements could be little, I mean they say about say for example, you have seen this sort of heights of landfills where the settlements are going to be very huge. Say for example, if I say about the possibility of the landfill settlements could be as high as 30%. Can you imagine? It is very difficult, like 3 meters could be the total settlements that one expect in some landfills, because the settlements in landfills is composed of 3 components. One is the immediate settlement under load, then the second one is the secondary compression, we call it in geotechnical engineering. Third one is called settlement due to all this material like biodegradation and all that. In fact, people have measured that the settlements can be as high as 20 to 30%. It is too big a quantity, like so it is not like 5% or 10% like what you expect in a typical case, say for, or even in the case of even 0.1% we expect in the case of well compacted materials. Okay. In the case of compacted samples, like if you have an embankment, you have to expect some sort of settlements that could be of the order of 0.1% of the total height. Here the settlements could be very high, 10%, quite because of the biodegradable matter being present. So definitely this dynamic compaction is very helpful in reducing the settlements, and in some places where these fields are old, biological decomposition is complete, dynamic compaction is very useful in increasing the unit weight and in reducing the long term substance. This is another important point. So, I will just mention about the types of compaction here, because the dynamic compaction is a term that is normally mentioned, but it can be classified into different categories here. One is called dynamic compaction, dynamic consolidation, dynamic replacement, rotational dynamic compaction, rapid impact dynamic compaction. Actually it is just based on the method that we do, nothing else, and but all are effective. What is this dynamic compaction? It is essentially the process of compaction of unsaturated or highly permeable saturated granular materials by heavy tamping. Assume that you have a sandy layer, maybe some areas in Chennai or some place where, or in west coast or east coast, you need to, you are trying to come up with big infrastructure there, and the soil there is in some places it is unsaturated or it is saturated granular material, and one can really use this dynamic compaction using this tampers, and the response to tamping is immediate, which is very good. What is dynamic consolidation? This dynamic consolidation is nothing but it is again a heavy tamping of the saturated cohesive soils. In the previous case we studied about what the candidate was as cohesionless soil. There is no cohesion there, the permeability was very high, the response is very fast. Here since it is a clay, the response to tamping is largely time dependent. We know that the clays have a tendency for consolidation, which is a time dependent phenomenon, and we have excess pore pressures generated as a result of tamping, and dissipation takes place several hours to days after tamping. So this is a difference, like in fact I must tell you the example that the whole Singapore airport, we call it Changi airport, whole thing was reclaimed from the sea. Say for example, there is a soil, if you want to, what do you do, you if you want to construct extend the land area, you try to bring lot of soft soil and dump into the coastal areas, and then it gets deposited, and they constructed that whole thing, then the soil is fully saturated and clay. Even some places in islands, you know, if you are living in an island, whether it is a soil, clay or sand, it is very expensive. You may get any other thing cheaper, but not clay and sand. So you need to, but then you need to really, you know, have a very good engineering method to say for example, there is a some between a couple of islands, they may even if you want to transfer some clay or a sandy material from one place to another place, it is very expensive. So people have been using reclaiming. Once you get that material, you must be able to reclaim, the thing is you must be able to construct the infrastructure very fast using proper ground improvement technique. If you have sandy soil which is very loose, you want to construct something on it, you should go for dynamic compaction, whereas if you have a clay, you should go for dynamic consolidation. There is another one which is called dynamic replacement, in which you have a heavy tamping of the large pillars of the imported granular soil within the body of the saturated soil. So, the original soil is highly compressed and consolidated between the pillars, and the excess pore pressures generated requires several hours to dissipate. Pillars are used both for soil reinforcement and drainage, like this here. So, like you just excavate, it is actually a dynamic replacement we call it. The term is something, these are all very lot of terminology is there, but the principle is very simple, that you have clay, then you have this material, then again compact it and push it, like you have this material. So, you are trying to replace the say for example, this material in this manner, and then you are trying to introduce a good material in the place of weaker place. So, that is what we call it replacement. So, that is also possible. Then what is known as rotational dynamic compaction is also possible, because people have done some studies where a new, they call it is a new method in which you have the use of free fall energy. Like we know that you just drop a weight, then there is a free fall energy, then you rotate it also, like in that same place there is a rotational energy also, like So, it is called rotational dynamic compaction. The technique increases the depth of improvement in, so while doing it, it has removal as well as compaction, the both are there. So, you can see that the what people have observed is that in the case of rotational dynamic compaction and the dynamic compaction, there are some small differences which showed that cone penetration resistance was generally larger than that observed in the case of conventional dynamic compaction, and the tamper penetration in the rotational dynamic compaction was twice as large as that of conventional dynamic compaction. Actually, what we are doing here is that like you just have a sort of a material here, you rotate and then do that, it has a both its impact is much here. You can see that you have some sort of rotation and tampings, both are there, and of course, this is some sort of a laboratory study, like you can do a simple thing, but it is people have seen that with some rotation as well as direct tamping, it can improve better. Like this is an example, you need to have some sort of an equipment for that. Actually, in many of these cases, the equipment is a very important thing, like you must be able to mobilize lot of equipment which can do the job very effectively. Otherwise, the it is very difficult, like the job should also be very big, so that you can justify the equipment, you can justify the posting of personnel, and there should be an office and all that. For small jobs, they are going to be very expensive and no contractor will come for this. Then how do you evaluate the performance of these materials which are improved using dynamic compaction? We will see that. As I just mentioned, the depth of improvement is proportional to energy per blow, like you have some weight, you have some energy, then that much of energy is important to the system, and how do you assess whether it is improved or not? Best way is that as a geotechnical engineers, we know before construction we take an SPT values with depth. So, for example, 20 meters is the depth of improvement required. You take SPT values or cone penetration values up to 20 meters, then measure them after improvement. So, that is the only way of improvement one can see correctly, like otherwise it becomes very difficult. And the dynamic compaction maximum depth, there is an expression that is given in terms of n into square root of w into h. This is a standard expression that is available in many of the textbooks available on dynamic compaction, where the depth of maximum depth is the depth of improvement in meters. N is a coefficient that caters for soil and equipment variability. N is a term, like see we say that WH is energy, but there is a small correlation N into square root of W, which is related to this depth. W is the weight of tamper in meters, tons and the height is height of fall in meters. So, the effectiveness of the dynamic compaction can also be assessed readily by crater depth and requirement of backfill. Okay. The another point that we would like to say is that if you want to compare the effectiveness of the dynamic compaction, we use this particular terminology, and also one can say that the depth of crater depth, say for example it has gone by about half a meter, yes, in other case it could be only 25 centimeters. So, you can say that looking at the depth of the crater, one can say that which method is better. Like this is a small n values, actually there are different coefficients of formula to be used in that formula. There is a, depending on the soil type, there are values are given by different investigators. These are all from field. Then as I just mentioned, the dynamic compaction generates surface waves with a dominant frequency of 3 to 12 Hz. Like if you are doing dynamic compaction, as I will be showing you in the video later, that it generates lot of sounds. The frequency is going to be quite high, and it is very difficult to for the personnel to working, or if there is a next to a parking residential area, it is difficult. So, these vibrations generate compression, shear and Rayleigh waves. As we know, any vibration induces these waves, P waves, S waves and R waves, right. So, as I just mentioned, Rayleigh waves contain 67% of the total vibration energy and become predominant over other type waves at comparatively small distances from source. So, Rayleigh waves have the largest practical interest for design engineers because building foundations are placed near the ground surface. So, particularly the Rayleigh waves should not hit the foundations that are there next to that, okay, next to the source. So, here the source means compaction. So, how do you assess this effectiveness or the problem with this vibrations? This is assessed in terms of the peak particle velocity. In fact, once there is a damping made, the particles will travel in the form right, the waves it travels in the form of waves, and it has certain velocity. Like you can pick up, say you can use some pickups here and there and then pick up the velocity. What is the velocity of the particle that is traveling, right. So, the maximum velocity is recorded, like the velocities have like if you put accelerometers they, and then you can from accelerometers you can get velocities and displacements also. Like it will have 3 components, x and y z, x, y, z, 3 components they will have, and sometimes measurement of vibrations is necessary to determine any risk to structures. For example, if you are doing a dynamic compaction in a particular project, and the next building person should say that, should not say that because of your dynamic compaction project all the glasses in my house broke. This is software office, and all the glasses have broken, and your ground vibrations have, because of the dynamic compaction, has given so many problems to my staff, and I lost lot of money because of your project. So, people should not say that. So, what should be done? Measurement of vibrations is the only way. Like as I just mentioned, in fact I did a case where your people are doing, there is a big IBM office here, next to that there is some big opening in which rock is being blasted out. They wanted to construct again apartments. It is a fractured rock, small lot of rock is existing, and they want to make foundations, again one more multi-story building next to an IBM office. Then the IBM office said that no, we should not allow this fellow to construct the house, this whatever structure he is getting. They got a stay, but then how was it resolved? The thing is that this man was actually he did not allow there is a court order that this fellow should not construct, but this fellow is in a hurry to construct the apartments because he took lot of money from all the people who are already interested in that. It is all development, it is actually big business. So, finally to see that is resolved, we have to measure the vibrations, and also like that fellow should not use vibration techniques. There are different types of like if you just rock blasting cannot be used. So, you should not use rock blasting, which is very unscientific, and it should not. So, there are different ways of blasting again, like it is called putting a liquid, and then if you put a liquid, what happens, it enters the fractured rock, then it expands, then the soil, the whole rock gets broken, then you can remove the rock pieces. That is a easier way of doing. So, this is one of the important ways in which one can measure the vibrations, and without vibrations measurements it is very risky. Like so, before, in fact, there we get lot of cases where, say, because of the traffic I have a lot of problems. So, you have to measure the vibrations before taking it up. Even if you are trying to construct a road or a big project, first take the velocity measurements, then construct it, and then if the measurement, like what I said, peak particle velocity, if you measure it, then if it is within acceptable limits, then you can say that my structure did not cause any difficulty to you. So, the vibrations can be estimated through empirical correlations or measured with the help of instruments such as portable seismograph, accelerometers, velocity transducers, linear variable displacements, etc. So, you have a number of equipment like this, and the relation between the peak particle wave velocity and the distance is like this. Say, for example, you have peak particle wave velocity and the distance. So, depending on the distance, one can like these are also here, the different parameters are given here, distance, the distance in meters, weight in tons, and height. So, all the parameters plotted, and then the maximum allowable range as per the German standard. Actually, this is as per the German standard, maximum allowable DIN standard for 4150. So, if the material falls in this range, it is acceptable, that is what they say. Like if it is very close, and so you should be able to really reduce weight and height and something like that. So, you must come out and see that this is practiced in some sense, otherwise that leads to lot of litigations. Like that is what according to German standards. Even in British standards, like they have some limits, like say for example, you have a reinforced soil reinforced structure, RCC structure, industrial structure, what should be the peak particle wave velocity? About 50 mm per second, or light unreinforced building or something like that, 15 to 20 millimeter per second. Then the other one, like small residential buildings, 20 to 50 millimeter per second. So, these are all some limits. In fact, there is also the effect of these vibrations on humans, like you do not want to tolerate this vibrations, you do not like. Even the earthquake, I think earthquake came and nobody must have slept in Delhi or somewhere, right. So, you see that if these velocities are so less, 0.1 mm per second is not noticeable, and you have a scale here, like right from being noticeable, not noticeable to highly noticeable, like you have a classification here. One should really measure this peak particle velocity. So, for example, the metro is coming up, one can say that because of the metro there could be velocities, right, vibrations induced into the next structures. So, in fact, not only from health point of view, it is only from even the health point of view of the structures that are there. If too many vibrations of small vibrations are there, there could be fractures developed in the systems. Small vibrations leads to a lot of problems. So, small is not that easy actually, it is like a small sound, very low level can make big problems. So, I mean people have understood that to some extent, and then they have been taking measurements, and this is a very serious problem, like it can affect health of persons and health of the structures and all that. So, monitoring and control is another important point in the dynamic compaction, and what we do here is that you can see that like this is the machine that can do that dynamic compaction, and it has a tamper with accelerometer and FM transmitter. This is one thing. Then you have a total station to measure tamper position after impact, like there is some surveying equipment which is sophisticated, which can measure the tamper position, you know, like you would be interested in the depth and what is the impression it has caused and all that. And WAN with receiving and processing unit, it is another one. Then you have a WAN with receiving and processing unit, you have all that data acquisition and all that. And what it gives is that what is that is going on, like we had some discussion earlier where you are trying to get about get the information about, it is called the chart for this particular location. You have a chart for telling what is the initial health of the this location, say for example 10 meters, in terms of the SPT values, in terms of the cone penetration values, water content, all that, and what is the health of the particular soil at up to depth, say for example 10 meters after dynamic compaction, and these are all, they will give the signature of the ground. The signature of the ground you are able to capture very well with instrumentation, that is very important. Then how do you go about design? See, actually one should understand that this is a technique that has been very effective, and the people have used it in some places, like compaction helps or dynamic compaction helps, they have understood, and they are trying to analyze, because the advantage of analysis is that you can design properly. So what is that we do in the design is that you can get the depth of improvement, you can know what type of energy you can give as an impact, then influence of cable drag, equipment limitations, like we should understand the equipments that are there, because you are planning for some energy level and that is in fact related to the equipment. Then influence of the tamper size, grid spacing, time delay between passes, because how much delay is, like as I just said, there is a difference between time, the dynamic compaction and dynamic consolidation. Because you need consolidation, you need to give some time there, that is a simple difference. Then soil condition. So the design must be able to address some of these issues, so that you come out with some rational design approach. What is the primary concern in the dynamic compaction is the depth of improvement, which depends on the type of soil, the energy per drop, the contact pressure of the tamper, then grid spacing, number of passes, time lag between passes. These are all the some of the important variables. And as I just mentioned, weight of the tamper times the height of drop is energy, and the main parameter in determining the depth of improvement is from this expression, which is from the free fall of the tamper, and it is D max is equal to n into square root of W into H. This is an expression. What is the influence of cable drag? The cable attached to the tamper, you have a, like you will see you have seen in the photos that you have a cable attached to the tamper, and it causes friction, reduces the velocity of the tamper. It is supposed to be freely, we said a free fall, right, like similar to an SPT test. If it is not falling freely, then the total energy into the system may not be fully realized. Then free fall of the tamper is more efficient. Yeah, that is what we want, because all the energy that you are trying to give should be totally into the system. There should not be any loss, like in the case of SPT test and all that, we have losses in the transfer of energy. That is why in fact the energy transfer in the case of SPT is about 50 to 60%, it is not much. So what are the equipment limitations, like why these things we should understand is that all people cannot do this. People should understand that the dynamic compaction is a technique. People should understand that the technique has to be followed properly, and the technique you can only follow if you have the knowledge of what goes into this method itself. So for example, crane capacity, the height of drop, the mass of the tamper size, these are all based on the equipment. Like grid spacing, the grid spacing is an important variable here, like as I just mentioned in the previous slides about a few minutes back. Depth of improvement depends on the grid spacing. If you have wider grid spacing initially, it means that you are trying to compact larger depths, and as you just go up you try to reduce the spacing, so that you have a good improvement even at the top layers as well. Then first pass compacts the deepest layer, that is what one should understand. The first one should be equal to the compressible layer. Actually see, in some places you should there are two ways, compressible layer it can be 10 to 20 meters. Like you need to have a criteria how much I would like to compact, is it 2B or 1.5B, 3B, like say for example 100 meters is the height of the width of the area. 100 meters you can't go 100 meters, right. You should just have, you should be able to do some sort of analysis where okay, you have a soft soil area and I did construct all the buildings there, then what is the load it is getting transferred to what point. Suppose I assume that the soil is soft, up to which point the stresses are going. Suppose I compact very well and then make all this very strong, the stresses will will not go deep. So you must be able to compare the actually stress gets mobilized when you apply load. What happens, shear strains get mobilized in the soil system. So you must be able to do actually a numerical analysis, a finite element analysis, or some sort of detailed analysis, like where you just impose a load and calculate the strains, say strains of the order of 0.1% or 1%, some sort of limitation one should have, similar to the depth of pressure bulb concept. So one should look at it, and if the material is going very deep, definitely you can't do a stone column or any of the ground improvement technique up to that. The objective is to restrict it to about some depth, which can be cost effective for you, very safe and cost effective. There are two issues here in ground improvement techniques. One is the safety. Number one is the safety, there is no other issue, safety and safety of the operations, safe. Then the then next is the economy. It is not without safety there is no economy meaning. So the generally what we do is that the significant passes compact shallow, subsequent passes compact shallow layers may require lesser energy. Then ironing pass compacts top layer. The time delay between passes is another important variable, and as I just mentioned, it allows the dissipation of pore pressures. So how do you assess this? In case of clays, you can put piezometers. Piezometers measure pore pressures and they help you to monitor the dissipation of pore pressures in each pass. One can do a lot of experimentation there, trial and error, and then do that. This is going to be very effective. So what I will do is that in the next class I will show you some video of how this process could be done, dynamic compaction could be done, and some case studies. And what I feel is that some of these points, they are all actually this dynamic compaction is somewhat empirical, but it has been very effective, particularly in US and landfills they used it to a large extent. As I just mentioned, even the whole of Singapore Changi airport is reclaimed from the sea and compacted using this method. I must tell you that one professor S.D. Ramaswamy, actually who did masters here in Institute of Science, and went later and settled in some places, and then finally in Singapore at the time. He was partly responsible for I mean maybe wholly responsible for doing that reclamation. It is called land reclamation of the Changi airport. So it is a very marvelous achievement, and people have, it is not easy. It is published in American Society of Civil Engineers journal also. So there are many case studies in this line, and the advantages of this technique is that the its effectiveness can be seen in the actual I mean by doing it, and the theory is simple. Theories are simple, but the practical advantage is very high. Say, because as I just mentioned, it is applicable to wide varieties of soils, and particularly municipal solid waste or waste dumps, or even sandy soils, and where there is more permeability, and clays it was done. And the effectiveness is essentially because of the here the principle is simple, that you are trying to tamp, which is a very layman's way of doing things. Like if you know that the strength is not there, try to put a lot of energy into the system, then it becomes stronger. So, with that background, people have, it has been a proven technique in many projects, and I am sure that we will have some more discussion on this in the next class. Thank you.